entanglement or removing it, which one wins, or hiding the information or revealing it, and which one wins, right? And so that's what it's about. Now there are many models that have been investigated by now in all sorts of different geometries, 1 dimension, 2 dimension, higher. You know, everybody interacts with everybody. And then you can put in extra symmetries or possibilities of topological order, all this kind of stuff. But I'm going to do the simplest case for today, just to keep it simple, which is 1 + 1 dimensional models with no symmetries. So sort of the generic cases, and that's what's in these 2 papers. And the model that's studied is the models that are studied in these papers and that are studied in a lot of this work are random quantum circuits. But being a random quantum circuit is not essential to this physics. People have also studied, you know, non-random spin chains subject to measurement, and they have essentially all the same physics. So the random quantum circuits are there, you know, we do them because they're nice to work with, not necessarily that their physics is that different from the generic case. Although I'm going to have 2 models, one of which is generic gates and one of which is stabilizer gates, which are special and allow you to do good numerical work, right? So I will be looking at a generic case and then a special case whose virtue is you can do really big numerics on it and really study the problem carefully. And that's non-generic, of course, right? You know, large many-body quantum systems whose dynamics you can study on a classical computer, that's non-generic, right? But fortunately, in this case, they contain a lot of the same physics, so we're able to use them. Okay, so here's our, I hope you can see this. I started drawing a little too small. 1 + 1 dimensional, right? Space, time, feed. It's a chain of qubits. Feed it in at the bottom here. There's a bunch of gates and a bunch of measurements. And in these models, and the ones I'm going to talk about, the gates are in this standard brickwork pattern, which is very nice for scrambling, as many of you know. So these are unitary 2-qubit gates. 2 qubits come in, 2 qubits come out at the top. And it's either a completely random unitary there or a random stabilizer unitary. The stabilizers are special unitaries that when they act on a product of Pauli operators, what comes out is still a product of Pauli operators, so they do not make operator entanglement. They make state entanglement, but they don't make operator entanglement. And that's what allows them to be simulated on classical computers. Okay, so we have a standard random quantum circuit, which I'm sure you guys have heard a lot about. And then we're adding in projective measurements between gates. So each qubit between a given gate and the next gate, it could be measured. And since our gates are going to be completely random without loss of generality, we can always measure Z, the Z component of the qubit, just because the gates are completely random, so that no particular direction is special. So let's just say that. And it's a projective measurement. The results come out with Born probabilities, whatever the state is. And a classical bit comes out. So this measurement happens. You get a result. You write it down. That's a classical piece of information. And now the state is, quote, collapsed to whatever that measurement gives. And that's a very nonlinear operation, right? Very nonlinear operation, okay? These, in the models we're talking about, the placement of the measurements is random. So every place a measurement could happen, it happens with probability P. So we have random gates and random locations of the measurements, and that's our model. It's in the, well, right. It's in the Z, I'm telling you, it's in the Z direction. That's not important because my ensemble of circuits have completely random gates. And so saying they're all in the Z direction is no different than saying, oh, some are in Z, some are in X, some are in Y. Or in the Haar random case, it's a completely random direction. For the stabilizer circuits, the X, Y, and Z are special directions, right? So by saying it's Z in the models I'm talking about, I haven't changed anything. It's just choice of basis or a gauge choice or whatever you might say. Yeah.
So these unitaries are all the same random unitary?
No, they're independent random unitaries, right? So every gate is independent random. Now we are, this is for this model, right? Yeah, the case you're talking about where they're all the same, that's a different model, and that's interesting. It's actually not, translate, what happens when you really put in translational invariance? Can you actually get to a different behavior? This is still not clear and hasn't really been looked at that carefully. It's actually something on my agenda. Somebody else had their hand up. Yeah. Well, you just write any, okay, so if you have a string of qubits, there are the Pauli operators are a complete set of operators. And so there are 4 to the n operators in a string of n qubits, right? And just think of that as a state, as if those were 4 basis states of a state. And then you can define entanglement just like you would for state entanglement. That's operator entanglement. It's just really entanglement in the doubled space that you have for operators. Does that make sense?
Take a state of the system, which then gives a space for your operators. You told us what's the Hilbert space of the operators.
No, I told you what was the set of all linearly independent operators. So for a single qubit, there are 4 operators, which are 1, X, Y, and Z. And consider those as 4 basis states. Yeah.
Then you want to discuss the entanglement.
Yeah.
Which I thought you might have planned from the explanation diagram. Perhaps that's not what you planned.
Well, I'm not really going to go there particularly. I just said that to sort of define what stabilizer gates are like, what special properties they have. But I'm not really going to use them particularly. So maybe, right, if this remains confusing, let's try to revisit it, but I think it might not be important for what I want to say today. Okay, yeah, right. So we're going to have, right, so this is the model, and we have a parameter P, which is the probability of, at a given place, I've decided to do a measurement, right? So we have an ensemble of circuits, which is a brickwork, independent random gates, and random choices with probability P that we're going to measure on each place, and that's a circuit. That's a given circuit, right? And just for scale, we're going to find that for both of the models I'm going to tell you about, the critical value of P is about 1/6. So the measurement rate, it's not very small. It's not close to 1. It's around 1/6. That's just a rough number, but it's okay. Yes. Okay. Okay, so as I said, we're going to have 2 models, and I basically said this already, but let me just say it again. So we're going to have the generic model. Gates are IID are random. So this means they're just sampled uniformly from all two qubit gates with no structure. And the first paper, they were doing the Haar random case. But then if you want to do, doing the numerics on that is hard because it's a real quantum problem. And so there's no shortcuts. And so if you want to do good numerics on these questions in a different model, you look at the stabilizer model. And we call it in our discussions LCF after those guys, Lee, Chen, Fisher. And these are just IID random stabilizer gates. Which are a discrete subset of these. I think for there's something like 11,000 something independent, or 11,000 different 2-qubit stabilizer gates. So it's not a small discrete set, it's a pretty big discrete set. And this allows large scale classical. Classical, I mean on a classical computer. So you can do good numerics on systems that are, with 1,000 qubits, a chain of 1,000 qubits run for thousands of time steps, that scale. So you can really do critical phenomena and scaling and get out to CFT data, stuff like that. Now, fortunately, this simplified model, I shouldn't say simplified, this numerically accessible model contains a lot of the same qualitative physics as the generic models do. There are some differences, some of which I'll mention, and they are in different universality classes, not surprisingly, and now we have good enough data to make that very clear that they're different universality classes. So these two models have a phase transition, not at exactly the same PC, but quite close. And those phase transitions are, as far as we can tell, new types of conformal field theories, non-unitary central charge zero field theories, sort of akin to percolation. And they seem to be a new type that's still not very well understood. And I'll try to say a little bit about that. Okay, so what we do is, what is done is we look at typical what's called quantum trajectories. And this is a term that's been around for a long time in quantum optics, but at least my education, it was neglected. I only learned about it recently. So if you run something like this, you do these measurements and the data comes out for the results of the measurements, and that defines what's called a quantum trajectory of that system, right? And we want to be just, set this up and run it and see what we get typically. Actually, I should comment this, what we're asking to do is just routine for the types of devices people are now building, like the Google Sycamore device or trapped ion computers. This is exactly what they do all the time, is do 2-bit gates and make measurements, right? And so there's nothing special here of what we're asking to be done. The tricky part is analyzing the data afterwards. It's the, so right, we look at typical quantum trajectories and ask, what are the properties of the quantum state? Right, so you run it, you get a given trajectory, given the data you have, which is, let's say the circuit, what gates, what measurements, the results of the measurements. and then you get a final state, what's the property of that state, right? And that's what we're asking about. Okay, and there's a phase transition. So we've got one parameter P. So let me draw the phase diagram. There's P, here's PC. And there's two, well, there's sort of a trivial point here, which is just unitary dynamics of a random quantum circuit, which scrambles and there's no measurement. So there's a special point here at the end. But then there's two phases here, and I give them three different names because there are three different aspects of the distinction between the two phases, having to do with purity, having to do with information storage or coding ability, and having to do with entanglement, right? So this phase here, which in some sense is the ordered phase, is mixed, and I'll tell you what I mean by that. And it's also coding, in that it's a successful quantum code, and it's volume law, in that if you have a pure state, it's volume law entangled. And then there's a phase transition, and over here, it's pure. And let me just briefly say this here. If you put in a mixed state at the bottom and run it in the limit of a large system, if you're at P greater than PC, you're going to get out a pure state. It purifies. Whereas if you're over here, it stays mixed. Okay. Here it's non-coding. So just quick summary, this guy remembers some quantum information about the initial state in spite of all these measurements trying to reveal it or collapse it and dephase it, whatever. Whereas over here, the measurements win, and the information about the initial state, quantum information about the initial state, is all lost. Some classical information about the initial state was detected by the early measurements. So it's not like all information about the initial state is lost. A little bit of classical information is kept because the early measurements succeed in revealing some of it. And then it's area law entangled. So this is always pure. And so given that it's pure, we can ask how entangled is it? And it's area law entangled over here. No, qubits. Well, yeah, we have to, it's a phase transition. We have to take the thermodynamic limit. Yes. Yeah. So it's large systems, long time. Well, the critical point, as far as we can tell, is conformal field. You know, it's dynamic exponent 1. The time scale's the same as space, like in standard conformal critical points. And that seems to be the case, at least in low dimensions. We don't really know the situation of what happens as you go to high dimensions in these things, because we don't, as I'll say, we don't know the upper critical dimension, and we don't know the mean field theory. Well, presumably emergent, right? Of course, it can't have full, it's a lattice, right? But it seems to, the numerics indicates under a lot of different tests that at the critical point, there's an emergent conformal symmetry, like is common in many phase transitions.
Will it remain the same?
Well, it's not relativistic. It's we're talking about Euclidean only at the critical point. Well, no, I don't think it has. Well, I guess it does, right? Right. If I had the two-dimensionalizing model where both directions are space and I boost it, that's just a scale change, and it would still have it. Yeah, and so this presumably does. So this is the Euclidean. Can you rotate it? Yeah, it seems to be isotropic. Yeah.
But the evolution really.
Yeah. It's produced by something which looks like it's got a special direction. But in the end, at the critical point, if you coarse grain and look at the long distance correlations, it seems like that goes away. It's not still there. It may be that it's only true for certain correlation functions, and for other quantities you might calculate, that's not true. I'm not sure.
Do I understand correctly that even though you have this unitary evolution, at the critical point it would be Euclidean theory?
Well, we don't know what the field theory is. That's one of the outstanding problems here. What we mean, when I say it seems to be a conformal field theory, is we go to the critical point and we look at all the correlation functions in space and time in the way.
The question is not with the word field, but the word conformal. Well, I think I have a more basic question. So whether it is whether correlators depend on t squared plus x squared or t squared minus x squared.
T squared plus x squared. Yeah, it's Euclidean in that sense, yes.
Reverse space and time. You view the circuit in the other direction. Right? Will you have also?
Well, no, I'm not sure I know what it means to run this in the backwards time direction.
Well, I mean, the unitary.
No, but the measurements aren't. They're totally nonlinear and non-unitary.
That's exactly what makes the word conformal so confusing. Because if it had been
Well, okay, so why don't you just ignore that for now? Because really all it is so far is if you look at the correlation functions at the critical point and test them with various cross ratios and all the usual stuff you test for conformal field theories, they pass the test, right? And then there's that's really all it is so far, right?
I have another question. So you said, but you didn't write, that one of them is ordered and the other is disordered, the two cases? That was said.
Yeah.
So
There's a way of viewing this where this is the ordered phase and this is the disordered phase. The entanglement over here is the free energy of an interface, like a Ryu-Takanagi surface, right? And it's an interface between two domains. Whereas over here, the interface has zero free energy, right? And so it's like an ordered phase and a disordered phase in that sense. But again, it's not, we don't know what the field theory is. What type of these are types of quote ordering, but I can show you what an order parameter is later. Yeah, so we have an order parameter, which I'll get to, I hope. Yeah.
this non-coding property after the phase transition, does that assume that you throw away the results of the measurements?
No. So when I say coding, I'm asking how much quantum information about the initial state is in the final quantum state, given that you know everything about the circuit, which gates, where the measurements were, and the results of the measurements. So you know everything. Can you decode some information about the initial state from the final state in principle, right? Of course, in practice, you probably can't decode it because that's an exponentially hard thing to do. And that's why this, although doing this is very simple for current experiments, analyzing the data is very hard. And that's actually one of the open questions. Is there a way to get at this phase transition which isn't exponentially hard in the generic case? And that's not clear right now because, although I can tell you exactly what the phase transition is, it's all properties which in the lab are exponentially hard to do in terms of analyzing the data, right? Not in terms of producing the data, in terms of analyzing the data. Tom? Larger fluctuations. Well, by what measure? What does this mean? I don't know. Over here, we have interfaces which have big fluctuations in them. Whereas over here, there's nothing but short range structure. So my initial reaction is there's bigger fluctuations here, right? I don't know, you know, like if I have a system with a continuous symmetry and I'm in the disordered phase, which has just short range fluctuations, and I'm in the ordered phase and there's Goldstone modes, which one has bigger fluctuations? Exactly, right. So I'm not sure how to answer your question. Yeah.
So David, does this have anything to do with directed percolation? I mean, directed percolation?
I don't, not that I know of.
So
There's a connection to percolation, which I hope to get to.
is there
Yeah, directed percolation is not conformal. It's very anisotropic. Yeah. So yeah, no, this is different. This is more a relative of conventional percolation, as I'll tell you. Yeah. It will purify. It will purify, yes. Exponentially, the time scale is exponential. In here, in this phase, the time scale to purify in a finite size system is exponential in the length of the system. Because basically what you're doing is you're putting interfaces across it, and those cost a free energy. Well, you don't get phase transitions unless you take the limit, right? That's my next point. So we take the limits. L to infinity. So L is the length, okay, the number of qubits, and T to infinity. And we want T much bigger than L, and T scaling polynomial with L so that we don't purify, right? So if T is polynomial in L with a finite power, then in this phase, it'll stay mixed in the limit, right? And so you have to take the limits this way. Well, you can also take the limit T of order L, and that's a different regime. You can still see the phase transition there as well. All the Renyi entropies. So the entropy of the mixed state, the entropy of the information it can store, and the entanglement entropy, and all the entropies, yes. And in fact, one of the Renyi entropies can even be volume law over here, as I'll say in a second, the zeroth one, the zeroth Renyi entropy. Maybe not a second, but in a little while. Yeah, but this phase, yeah, it's all Renyi entropies. Over here, you have to be careful about which entropy you're talking about. Okay, so you have to take the limits. And if you don't take them, there's various ways of taking the limits, but you have to, Okay, so let me just summarize some of the statements about these phases. So the, in some sense, more interesting phase, which is this one, stores information. It's got volume law entanglement. This one, this one's sort of boring. Okay, so this phase, which I'm calling mixed or coding or volume law. Okay. Non-zero density of, so QI is quantum information about the initial state is present at long times. So it is storing information about the quantum information about the initial state, a non-zero density. So it's what the quantum information people call, or coding people call, a finite rate code. So we have a system, and we're not just storing one bit of information in there. We're storing a non-zero density of information. Okay. Okay, and it's well encoded, right? It's clearly well encoded because it's subject to these measurements. Steadily, these measurements are trying to get that information out and they're failing. And so the scrambling has won. So the scrambling won. So the system, this simple physical system sort of spontaneously makes an interesting type of good quantum code, finite rate quantum code. This here, yeah. Yeah, right. So as long as time is scaling much more than L, you get a behavior which isn't dependent. Say we're going, T is going as L to the power, and the power is bigger than 1. What you're going to see is not going to depend on that power, right? But once you get down to the power equals 1, then what you're going to see is going to depend on the ratio of T to L, right? Because then you're probing the relevant timescales for that length scale.
Just make sure I'm saying it's a different P, right?
Sorry. Yeah. Or whatever. Yeah. Yeah. So if I have T, the ratio of T and L, some number of order 1, then we will see different behavior depending on that ratio, because that's the relevant scaling variable that changes the critical behavior. Well, as is standard in conformal field theory. Okay, so now we have to ask, do we have open boundary conditions? Do we have periodic boundary conditions? Let's have periodic. And so now we're talking about a conformal critical point on a cylinder, and you know from conformal field theory how the correlation functions behave when you go up to far along the cylinder. They decay exponentially with a decay rate that depends on the radius, right? And so all that stuff's been looked at, and it seems just to do the standard stuff in conformal field theory and finite size systems. Yeah, well, much smaller. Once they become of order, then they start depending on it. Yeah. Standard finite size scaling. As far as everything's been checked, it's just standard type finite size scaling for things that are conformally invariant, and people have checked these various cross ratios and things like that, and it all holds up. But that's numerics, right? That's numerics.
Sorry, what is known about it?
It's continuous. We have estimates of the critical exponents. We have CFT data numerically. So there's a catalog of numbers that are known. It's all continuous. Yeah, it's not first order, right? We haven't found any first order transitions here. So in 1 + 1, it's pretty well studied. What happens, like I say, as we go to higher dimensions, as we go to random graph type situations where there's no spatial geometry, where you would normally get a mean field type behavior, we haven't been able to make that much sense of it yet, right? And so what happens in higher dimensions and in, we don't have an upper critical dimension, we don't have a mean field theory, which might just reflect how hard we've worked. It's not clear what the situation is. Okay, it's a lot of open questions here. Okay, so now I'm talking about this phase. It's got 3 names, and so I'm going to tell you 3 things about the phase to go with each name, right? So this is the statement about it to go with coding, right? It's a coding phase, and it has this property that stores information well encoded at a non-zero density. If initial state was mixed, it remains mixed. So that's why we call it the mixed phase, right? So if we give it initial conditions that are mixed, it stays mixed here. Here it purifies. And then if the state is pure, right, of course, we could put in a pure initial state. It has then at long time, it goes to volume law entangled. And these are volume law. This is volume law entropy of the mixed state. This is volume law density of quantum information. And that's true for all the Renyies. So not just von Neumann, all the Renyies, including 0 and also infinity, I think. Yes, including 0 and infinity. Yeah.
Can I ask you on the well-encoded question? So suppose that I sit at some point like the deep in the mixed state, and I change the number of qubits. So I go from like that.
But well, you mean measuring a operator that sits on multiple qubits? Yeah. See, now that can produce entanglement. So if we're in this phase and you do that, you might go into the other phase. And we've looked at models like that. So there are so-called measurement-only models where you don't have any unitary dynamics. You just have measurements, but they're multi-site measurements of operators on multiple sites. And you can make those models do all the same stuff. So exactly where the scrambling is coming from, whether it's coming from a unitary or whether it's coming from a measurement that produces entanglement, that doesn't seem to be important so far. Yeah. This up, can I do a third one? Yeah, looks good. Yeah, go ahead. Yeah, and that's a good argument for why it shouldn't make any difference. That it's not really very different, right? Right? No, you're absolutely right. Yeah. So it's not surprising that things that only do measurements can do the same thing without having explicit unitaries. Okay. So that's the ordered phase. And let me just say, so the other phase is P greater than PC. And here, the quantum state of the system goes to pure and area law entangled. At the critical point, the entanglement is logarithmic, as is known for conformal field theories, logarithmic in the length. Okay, so it's pure area law entangled, and it's determined by recent gates and measurements. So this.
When you have the low dependency of entanglement.
It's the, what do they call it? The effective central charge, because it's a C equals 0 conformal field theory. So it's not the usual relation with the central charge, it's the effective central charge. And that's something that Cardy and company have really worked out, say for percolation and other disordered models. And this seems to fit into the same story. So the effective central charge is what is it? It's the derivative of the central charge with respect to the replica number. The central charge is 0 in the limit you're working in, but then you take the derivative, and that's the effective central charge, and that ends up coming into the entanglement. If I said that correctly, please correct me if I said it wrong.
It's also C minus 24, 12 times lowest state. You have a set of primary. C minus.
Well, is that general for all non-unitary C equals 0 field theories? I don't know that that's true. Yeah. Yeah, I consult with Roman Vasseur and Andreas Ludwig about this, and they've never suggested making that test, because I think it might not apply to these cases, which are quench disorder systems. But yeah, I don't know either. Yeah, sorry, that's not. Okay, so if you look at the state that comes out the top at some late time, the information, in order to reconstruct that state, what it is, you can pretty much reconstruct it with knowing just the last certain number of layers of the circuit, where the measurements were, what the results were. And that's pretty much predicts with high fidelity the final state. Okay, so it doesn't have any long-term memory anymore. It's just reflecting recent stuff. So all quantum information about the initial states gets lost. And as I said, some information about the initial state, some classical information about the initial state is there in the measurement record from the early measurements. So the very first few measurements will produce data about the initial state. And so you'll have a little bit of classical data about the initial state in the measurement record, but none in the final quantum state. Yeah.
You use the phrase energy momentum.
Did I?
A well-defined operator here, which is the energy momentum tensor.
I didn't say that.
Maybe you didn't.
Did I?
You talked about how things behave the same as in a conformal. Maybe I'm extrapolating from what you said. Is there a well-defined energy momentum?
I don't know. I'd like you guys to tell me. Yes, not that we know of. Not that we know, that's a basic question here, is we've got something, there is some field theory here, and we have numerical evidence that this is some sort of conformal field theory, but we don't know what the field theory is. Right now, there's a...
Surprising that it doesn't seem like there's a Hermitian kind of point that performs the evolution, because the evolution is not unique.
Exactly. Yeah, yeah.
So
yeah.
I don't see how there could be an energy.
Yeah.
But then what is the generator of the performance?
Yeah, right. No, I think this is why Juan asked me to come tell you guys about this, is because there's a lot of interesting questions here, which I want to tell you about some of the questions, but I'm not necessarily going to tell you about all the answers because I don't know them. Yeah. There's something generating, the energy is what generates the dynamics, right? And there's something generating the dynamics here, but it's not Hermitian, it's not unitary, right? And so, but somehow it coarse grains to something that is acting somewhat unitary. Well, except maybe not, right? We're talking about a non-unitary conformal field theory with central charge 0, right? And so do you always expect to have proper definitions of the energy and momentum in those cases?
I thought that even in non-unitary, there's a preferred operator.
Yeah. Right. No. So. Yeah. Well, if you really want to have a good discussion with this, invite either Roman Vasseur or Andreas Ludwig to give you a Zoom talk about it, because they've really been seriously thinking about this, as conformal field theory experts. But that's not my strength, shall we say. Well, okay, so there is a certain limit. There's a limit of this model where it maps exactly onto percolation. And percolation is an example of that, right? And then you can perturb away from that in that framework unfortunately, the perturbation you're adding is irrelevant and it flows off in an uncontrolled direction, right? And that's really the situation theoretically, right? And so, and then we have the numerics where we just test it and it just behaves like, you know, if you do all the standard things which Cardy and company have figured out for dealing with these C equals 0 unitary conformal field theories and doing their, you know, analysis of their critical points and their conformal, you know, and we do all that stuff and it all looks fine, right? Of course, it gives different exponents because it's a different universality class than ones that have been looked at before, but it all looks fine, right? As far as we can tell, right? And so that's really the situation. You know, there's a theoretical way to head towards these models as a field theory, but there's no control of it, right? It's just our you know, you have percolation, you have a relevant operator, and that flows you off to this landscape, but there's no control on the calculation, right? It just tells you it's that way, right? And it's true, it could flow off to something which was something totally different, but the numerics suggest it doesn't, other than just in the specific CFT data. That's sort of where we are. Yeah.
You mentioned when you're discussing how entanglement behaves based on conformal theory, and so you say that there is this critical point. Let's say there are two different. Is it clear that these two displays the same thing? And so I think that this conformal theory is having
Well, it's certainly not clear. Yeah. Yeah, no, we're looking at the entanglement of this actual physical state that's coming out, right? And it's true, you're right. You know, whatever this conformal field theory is, and you ask for its entanglement, it's not necessarily that, right? Yeah, that's true. Yeah. Well, yeah, that's what makes this non-trivial. Yeah, because if we didn't have that, none of this would happen. Yeah, yeah, no, the nonlinear, yeah, you know, people also study non-unitary models, which are linear, right? And they have things like this, but it's different. It's, you know, those are different. There are phase transitions there. Yes, yes, yeah, and that's also a big activity these days. And how these two, how that stuff and this stuff relates is, you know, I think that's still not entirely clear. No, but I think you can make, you know, non-unitary evolutions which will decrease entanglement. Yeah, and get phase transitions like this in systems that are linear, but non-unitary. See, this system, you know, the systems that are linear and non-unitary, they don't stay normalized, right? You put in a mixed state with probability 1 and you get out something which isn't even a probability, right? Whereas this thing, what we get out is a proper state, properly normalized. So the probabilities are you know, being done properly, but we have this nonlinearity, right? And so the two approaches, you know, yeah. And of course, this is, you know, this is like a standard thing you do in the lab, whereas, you know, non-unitary evolution is, you know, like where are you going to get a non-unitary operator to evolve your system? You know, they're just not around. It's as far as we know, this is all new CFTs, 1 + 1 dimensional, and that's one of the striking things about it. It's just 1 + 1 dimensional where, you'd think you'd know most of them, right? And here's another one. Well, the ones we looked at seem to, I think they're all power laws. Yeah, well, people call, okay, yeah. You guys are grilling me too much about CFT, and you're just asking the wrong person. And I hope Juan didn't have the impression I was an expert in CFT when he invited me here. Yeah. Okay, so let me just mention one thing in passing, which is a difference between these two models. So in the Haar random model, in some cases, in particular the case that Skinner-Ruhmann did, there's actually a second transition, PC, let me call it P0. And so in this pure non-coding area law phase, there's actually a transition where over here you have volume law Hartley entropy, entanglement entropy, et cetera. And that means the 0th Renyi entropy, or the rank of the entanglement, is volume law, whereas here it's all area law. So this phase here can actually be a product state where there are places to cut it with strictly 0 entanglement. So it's not just area law, but if there's certain cuts where the entanglement is 0. But in this interval in the Haar random, or the generic Haar random model, between here and here, there are no such cuts. And if you do a cut and look at the rank of the entanglement, it's volume law. All the other Renyis with index bigger than 0 are area law. So that's just a statement about the spectrum of the entanglement. So that's just a special feature that's in one of these models and not the other. The stabilizers have the property that all the Renyis are exactly equal. The entanglement spectrum is completely degenerate. And so all the Renyis are exactly equal. And so this just can't happen in stabilizer models. Okay. Yeah. And as I said, if you go to the transition, it appears to be some new non-unitary C = 0 logarithmic CFT, but not well understood at all. Okay. So let me now try to talk about this. How long should I go on? Well, people can leave, right? The doors are open and so let me so where do I have it here? I want to say a little bit. If we scale as t goes as L to the gamma with gamma, so if I do this scaling with gamma bigger than 1, the results you get don't depend on gamma. And that corresponds to, say we have it on a cylinder, that corresponds to a long cylinder, right? But once gamma gets to 1, because it's conformal, now the results are going to be sensitive to the ratio of T and L, because we're probing the timescales for that system to go to sort of its steady state. this is a process that, if I say at PC and just run it, it goes to a statistical steady state at long times. And the time it takes to get to that statistical steady state is of order L, right? And once I'm on timescales much larger than L, and even better, L to a power bigger than 1, then I'm just in the steady state. And the results are sort of independent of the time. Okay, so I just want to mention one piece of work. So I've sort of mentioned this already. So there's this paper from one. Okay, so what they have done is you take, instead of qubits, you take qdits with q states. So instead of q equals 2, which is a qubit, have q states, and then take q to infinity. And the measurements are measurements which measure which of these q states is it in. So they're projections onto single states when we take this limit. And this then goes to percolation. So basically, this transition, I didn't say that here. So this transition from area law Hartley entropy to volume law Hartley entropy, even for qubits, can be exactly mapped onto classical percolation. And what happens is you take this limit in the generic model, these two, this transition and this transition merge, and what remains in the limit is classical percolation. And that's a mapping that can be shown. Excuse me? Let's take q to infinity first. No, there's no scaling of q with n. Yeah. Let's take q to infinity first, right? And then just analyze the q equals infinity limit of this problem. And when you take that limit, there's a lot more things you can do. When you're doing Haar random, q goes to infinity, basically every gate maximally entangles. Right? Actually, let me just draw the picture. So what happens here is you have this circuit. So here's the gates. Every gate in this limit, every gate maximally entangles. And then if I have a measurement, we can just view that as the measurement completely disentangles, right? No, there's no entanglement between this and this if it's been measured, right? And so basically you have this graph of connected gates. It's a square lattice really, and the measurements just cut the bonds, and the phase transition is when you go through the percolation transition. And you can show that if I ask what's the I go up here to the final state, and then I cut out a region A and ask what's the entanglement of A with the rest of it. The entanglement will just be the minimal surface going through here, which cuts the fewest numbers of bonds, and you will get log Q of entanglement entropy per bond you had to cut. But the measurements have already cut a lot of the bonds for you. So if you're over in the high P phase, you can get through, and there's no entanglement entropy, or no volume law entanglement entropy. So it's the usual story you've seen. Okay, so they're able to show this, and then they do 1 over q. So they ask, oh, let's back off from this q equals infinity limit. And it's a type of, and you'll have to read about this. So it's a double replica. So in order to do this field theoretically, they introduce two indices and take two limits. So it's sort of a doubled replica scenario. And they're able to analyze it, but all they can tell you is this is a relevant perturbation to percolation. It flows off, and there's no control on where it goes. And you can do this not just in 1+1 dimensions, you can do it in general, in any dimension, higher dimensions, and it's always relevant. So it's sort of, in that sense, related to percolation, but not very directly, right? You know, it's sort of just saying you can flow away from percolation to this, right? And so we have, so far, we have no upper critical dimension. And no mean field theory. And a lot of effort has been spent on studying models where instead of just gates, you know, you can have two-site gates, and you can just have a bunch of qubits, and the two-site gates just randomly connect one qubit to another with no geometry. And that you'd think might give a mean field theory for this problem. And a lot of effort has been expended on studying those all-to-all models, but we haven't been able to get out a mean field theory yet. Okay. So we have a, let me just, so the things I have left to say, we'll decide whether I should. So we have a project underway with a number of people, it's actually centered at Rutgers in Jed Pixley's group, doing the numerics quite carefully for these two different models and getting out the CFT data and comparing it to percolation. And the three are three different CFTs. You know, the data are different, you know, and they're actually kind of close. So we had to work pretty hard to get the error bars down to see that they're different, but it's quite clear now that they're different. The generic model, the stabilizer model, and the percolation, they're all different in their CFT data. So that's some work in progress. Right. Now you might ask, what's the order parameter? I call this an ordered phase. What's the order parameter? And that actually, we struggled with that for quite a while. You know, you'd think, oh, what's the order parameter? It's these entropies, right? But the entropy is not an order parameter, it's an interfacial tension. You know, you guys know, if you ask what's an entanglement entropy, it's the free energy of an interface, right? And that's the interfacial tension, that's not the order parameter. And so to get the order parameter, and this is something Michael Gullins and I figured out eventually. I remember I was constantly going to these guys and saying, what's the order parameter? Tell me what the order parameter is, and they didn't know. But you know, it's sort of obvious afterwards. And so what you do, you know, you have your system. So again, here's space, and here's time. And what we do is we run it for a while. So we're talking about an order parameter in the, say, coding phase. You run it for a while, and then you take a qubit in the bulk, right, away from the initial condition, and if it's got edges, away from the edges, and you put this in a Bell pair with a reference, right? And this reference is just sitting there. It's not subject to any dynamics, but this guy is subject to the dynamics. And then you look at much later time and ask, how much is this reference entangled with the state at later time? And that's what plays the role of the order parameter. And then similarly, you can do two-point functions by you know, various constructions like that. So the order parameter is, you know, it's sort of, in some sense, the probability that a qubit of quantum information that you put at a given point in space-time, that it survives to later time. and it's kind of analogous to the order parameter in percolation. You go to a particular point and you ask, is it connected to infinity? Right? So that's a statement about the order parameter. Yeah, and I think those are all the things I wanted to say. We had plenty of questions, but we can certainly have more.
When you do these numerical experiments, what is the thing to calculate? Like, what are the operators to calculate?
Okay, well, there's two types of numerics that are being done. So most of it is in the stabilizer models where you can do really big systems. And then you're doing some very specific numerics that's peculiar to the stabilizers, where you do this, the stabilizers are Pauli operators, which are products of Pauli operators on many different sites. And then you update what's called the stabilizer tableau. So a given state is represented by what are its stabilizers that it is an eigenstate of. And then you update this stabilizer tableau by doing various operations in Z2 algebra. So you have these matrices full of zeros and ones, and you operate on vectors full of zeros and ones, and all the arithmetic is Z modulo 2. And then you can calculate mutual information or entanglement based on like the mutual information between a given set of qubits here and a given set of qubits here is counting the number of stabilizers that have footprints in both of those regions.
But the main observables are entanglement entropies of subregions, or Von-Neumann entropies of subregions.
Well, we look at entropies, we look at correlation functions of these types of order parameters. We look at purification rate. So we started off mixed and watch it purify. So the dynamics, one of the interesting things in the dynamics is, like if you're at the critical point, actually a very nice way to get the CFT data is to just go to the critical point and watch it purify. And the rate at which, if you have 2 qubits of information in the system and the rate at which you lose one of them, that is one of the exponents in the CFT. One of the operating. And then we, like now we're doing studies where we insert this and we look at what's called code length. So you put in the information on one site and watch it spread. So you look at later times and ask, oh, how big a region do I need in order to get the information? And that's called the code length. And so we look at the dynamics of that. But yeah, a lot of it is looking at entanglements and mutual informations, because that's what this is good for. Now, when we do the generic model, it's really just numerics of just taking a general quantum state and just evolving it. And it's really brute force. And that scale, and that we can only do quite small systems because it's,
Is there an analytic way of doing that random?
not in the presence of the measurements, no. No.
Entanglement entropy, we can resolve C, right? But you said we also know the C of this.
Well, the best way we're getting it now is the entropy of the measurement record. The finites, you have these things where the free energy has a term in it that's got, C divided by some constant divided by the length times the time. And so what we find at this point seems to be the best way to get the C effective is, we just run it and get the entropy of the measurement record, which is basically, that's the free energy. That corresponds to the free energy. And then you do finite size analysis on that.
C effective or C?
You can get C effective, yes.
So
Yes.
how do you get C?
Well, C is 0. How do we know that?
How we know is C effective from
Yeah. Do we explicitly show that C is 0, or do we just assume that?
There are many.
That's a good question. I'm not prepared to answer that.
There are many
Like I say, you should. Well, not exactly, right? We have a limit where it becomes percolation, but we know our system is not that fixed point, it's some other fixed point elsewhere. So, that doesn't prove that it's also C equals 0. Yeah.
So what is C effective with this other?
I can't remember the exact number.
For percolation is 1.
It's different than what it is for percolation. We have that data. I didn't bring it. We hopefully in the not too distant future will have a posted paper showing all that stuff. That the numerics finally are going quite well. It took a lot of work, but
Say you computed this correlation.
yeah, you can get the not only the C effective, but the first couple of the scaling dimensions. Yeah, I was trying to think of the right word. Scaling dimensions. The first few operators. And then we know what they are for percolation exactly in 1 + 1, and then they're the first one is rather close to percolation, but now our error bars on the analysis are small enough so that they're different, and the stabilizer model and the Haar random model are different also. Ed?
Suppose instead of measuring a qubit with probability, you throw it away with probability. Is that also?
Well, I would think after a while you'd have no qubits left. We're running it, the number of measurements is much larger than the number of qubits, right? So that doesn't allow us to take the limit we're taking. No, you're not projecting onto a random thing. You're projecting it onto the thing that comes out with the Born probability, right? So it's not really random, right? It's dictated, its probabilities are dictated by the state. Yeah, there was an initial argument that the measurements have to win in the end. It's because the reason they don't is because the thing is a good code, right? If the system wasn't scrambling and hiding information, the measurements would win. And the reason they don't win is because it does successfully hide the information. And eventually all the information that's left in it is well hidden, and the measurements aren't learning anything about that quantum information. And there was an initial paper by some authors that gave that argument, saying, oh, there can't be a transition, it must always purify. And that was the flaw in the argument. And V2 of that paper is very different from V1. Maddie?
I'm still confused. Is it the CFT for all values of P or only at the critical point?
Only at the critical point. Only at the critical point.
And what is the operator in that CFT that takes the vector, right? So if we stick to
I don't know what the CFT is. I don't know what its content is. So, like we have some scaling dimensions, and we can, we can say, oh, it's probably this operator. But what does that tell us? What does that tell us?
The numerics, you identify the black spot.
Yeah. The first one is the order parameter. Yeah, even the second one, it's not completely clear. One thing that happens, so in percolation, there's the order parameter, and then the next one is the thing that you'd call the energy, right? The second operator. Whereas here, there seems to be some other operators before you get to that one. Although, that's just numerics, right? It's like the first one is rather close in scaling dimension to the order parameter. The order parameter for this and the order parameter for percolation they're pretty much, pretty close in scaling dimension. And then there's a big jump up in percolation to the energy, right? Whereas in these, there's more operators, right? And in fact, the second one has a scaling dimension almost twice the first one, right? And I think it's because in percolation, there's only one bit of information. Percolation is just telling you, are you connected or not, right? Whereas these things, they can hold many bits of information. So I think the second operator is 2 bits. The first operator is 1 bit of information. The second operator, in some sense, is 2 bits of information. And its scaling dimension is almost exactly twice 1. And then the energy is up quite a bit further, and we actually don't know where because it's confusing.
But imagine you see the PC and you change the value of P a little bit.
Yeah.
You check scaling towards PC. What is the exponent there?
It's very similar to the corresponding exponent in percolation. Yeah.
And that's not.
And that seems to be the fourth or, the thing is, we can get the first maybe 3 or 4 scaling dimension operators, and we probably haven't even gotten to that one yet. And I think it's in some sense because what we're talking about here, it can encode a lot of, its order parameter space is much richer than we're used to.
What is surprising is that
But this is all speculation, right? But what we see is, we see the order parameter, and then there's one at roughly twice the scaling dimension, one at roughly 3 times, but they're not exactly 3. But my feeling, but it's just purely conjecture, is there's a more complicated order parameter space, and there are things which hold 1 qubit and things that hold 2, things that hold 3, but that's just speculation.
All of these are operators with dimension less than.
Yeah. This is all much less than 2. Yeah. So there's a lot of relevant operators as far as we can tell, just by doing the standard analysis and just.
But that's what's so surprising. You move from between 2 points and you succeeded to hit that fixed point where the direction you seem to move along is not one of the lowest dimensions. Normally you would say.
Yeah. Well, these are all order parameters, right? There must be some symmetry. And we're on the 0 order parameter manifold, right? And so these, they must all be order parameters, right? That's because of what you said, right?
It doesn't seem to have any symmetry. That's what's surprising.
Well, it must. It seems to have some symmetry, but it's presumably some sort of, one way. It's probably can be described as some sort of replica symmetry, but we really don't know. This is. It's not.
Question is, can we activate the lighter operators?
Well, what do you mean activate them? You mean
Turning them on.
put a field on them, right? Because I know how to put in the order parameter.
Right. But what about the other lighter ones? You said there are many more relevant operators.
Yeah, I guess we haven't really looked at that, but I would, I don't know. Yeah, it's interesting, right? If I took two nearby qubits and coupled them to 2 references, that could easily couple to the second operator, right? We haven't done tests like that. Yeah. No, there's some. Yeah, we do. Yeah, that result about the the second scaling dimension being roughly twice the first. It's not in the literature. That's just the numerics we have and haven't presented yet. And but yeah, it's an interesting. Yeah, there's a lot of open questions here, but it's.
There are no more questions. That's not David again.